All right, hello everyone. My name is Scott Grisard. This is quiz review for Quiz 8A, the 5 p.m. class. I hope you all are doing well. So let's talk about this quiz a little bit. Oop, that's not it. I'm sorry, 5A, not 5B. I'm not sure which I said. All right, so this question here, this first question, first question is the linearization, right? So the linearization is just this formula. You could have left off the f and a and just had the L of x. So it's L with two parameters of x equals f of a plus f prime of a equals x minus a. All right, well, that's nice. So let's look at this thing a little bit. L f a of x equals f of a plus f prime of a times x minus a. Let's let a be x naught. I don't know. Let's give a name. So if we're doing an x naught, let's let f of x naught equal y naught. And while we're at it, let's let f prime of x naught equal m. So I've got L f a of x equals y naught plus m times x minus x naught. Why not just say LFA of x equals y? And I'm going to move the y over to the other side. So I've got y minus y naught equals m times x minus x naught. So what is the linearization? Anybody? What is this function? Bueller. It's an equation for a straight line. In particular, this is the equation of the tangent line. In other words, the linearization is nothing but the functional form of the tangent line. And it turns out that this little trick, this linearization, turns out to be a great generator of ideas. So, like tonight, we're going to be talking about, let me pull up the class notes here. We're going to be talking about linearization, gives you things like Taylor polynomials or a direct application of it. The intuition behind L'Hopital's rule, a direct application of it. Differentials and inverses, the derivatives of inverses. You get these things from this idea of linearization. And then concavity, convexity, a concave up or concave down is what we're going to call them. All of these ideas, and this is the big idea, one of the big ideas in Module 3, which I know you aren't thinking about yet. But this linearization just lives at the back end of everything here. So it's one of those kind of key thoughts. It's not really emphasized, but it should be emphasized more than it is. Because if you understand linearization, you can kind of start to see how the ratio of the linearizations is going to give you L'Hopital's rule. And, I can make other approximations. Those are Taylor polynomials. And that goes off to Calc 2, physics, all this other stuff. And then you get differentials, and that gives you a kind of a nice, very intuitive way of approaching all these things. So differentials are nice. They're kind of, we're going to be like, not but we're going to be like hand wavy. Yeah, and it looks like this, and it looks like that. So we're going to, we're not going to dig into the proofs, but they give you a nice way of thinking about stuff. So 1 to 5 there. How do we feel about question 1? Okay. All right, so question 2, I actually messed it up this morning. Question 2 is one of these over-decorated derivatives. All right, so be careful with them because they're easy to mess up. All right, and they're tricky. They're not hard per se. I mean, as much as anything is hard, they're not harder than anything else. It's easy to trip. So let's look at this. When we have this piece, 1 over 4 to the cube of the cube root of x to the 4th. What I'm going to do is I'm going to convert this carefully. 1 over 4, and then I'm going to have x to the 4 over 3. And I cannot tell you how many times I put that 3 on top and the 4 on the bottom. And then what I've really got here is 1 over 4x to the negative 4 over 3. And this 2 root x cubed over 3. Right? This thing right here is equal to, and this is what I messed up this morning, 2/3 x to the 3 over 2. I think I accidentally put 2 over 3 this morning. So they're easy to mess up. Don't, be careful with them. All right, so I graphed the tangent line. The important thing is that it goes through here. It looks kind of like that. Now, I'm going to compute this derivative. When I do it, again, I do the power rule conversions, and I be very careful. Now, note that this right here is a constant, and this right here is a constant. Right? 2 to the square root of 10 isn't going anywhere when I nudge x. Neither is 1 over j, which is Jenny's constant. So I've got negative 4 over 3 times 1/4 x to the negative 4/3 minus 3 over 3. That is the minus 1. Plus 3/2 times 2/3 times x to the 3/2 minus 2 over 2. Minus 0 minus 0. And yes, I do need to show where the zeros went. Okay, somewhere in there, I need a plus 0 and a minus 0. I need to show what happened to those things. Now, here I add these things. Remember, the only simplification I have to do is this. But since I see part B down here where it's going to ask me to, plug it in and do the slope, I'm just going to go ahead and cancel some of these terms to make my life easier down here. Carefully, those 4's cancel, the 3's cancel, the 2's cancel, and I'm left with negative 1/3 x to the 7/3 plus x to the half. Any questions about that one? And I'm going to say, does my work? So what I'm going to do here, in order to get the slope of this line, I'm going to plug in f prime of 1 here. And I get negative 1/3 times 1 to the who cares plus 1 to the who cares equals negative 1/3 plus 1 equals 2/3. So yes, the slope I drew is about 2/3, as it should be. Okay, so 1 to 5. How do we feel there about question 2? The exponents up here are just, you have to be careful. There's nothing else to say. You just have to kind of be careful. Annoying little things. Where is everybody? I see 20 people here today. Is it that Monday? Everyone's just like, oh, I'll go on Wednesday. Any questions about that? All right. By the way, Jenny's constant is J equals pi squared, blah, 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 blah. This is what it works out to be as the decimal expansion, hence Jenny's constant. Some graduate student got bored. Okay. Someone's asking questions about the test. I'm not going to answer those, except if you watched last night's test review on Twitch, you'll see the answers to that question, especially. Okay. All right, so I've got a sphere. And I've got the formula for its volume. So here's what's going on here. The radius is expanding, right? So the sphere is getting bigger. Air is being pumped into the thing. Surface area getting bigger, volume getting bigger, radius getting bigger. And my question is, how quickly is the radius expanding at a certain time? All right. So I know I'm pumping 2 cubic feet of air per minute. And let's say it's a spherical balloon. It is a spherical balloon. And the question is, what's the rate of expansion of the radius? So I list my variables here. I have some volume, cubic feet. I have a radius. I have time. That's that per minute thing. I have a couple derivatives. I have some data here. I got a 2 cubic feet per minute there. And I've also got this V equals 4 pi over 3. But this is not fixed, right? The volume is not fixed. The volume's getting bigger, which means that that's not motion picture data. That's not movie data. That's not, that's at a particular time when I hit pause, right? That's not fixed. That's moving. And then there's some time when I'm going to hit pause. All right. I'm going to take a snapshot at a particular time. So I have my V here, and nothing's fixed, so I'm not going to sub in anything. And I'm just going to take the derivative of this expression. And when I take the derivative of both sides of the expression, I wind up with 4 pi r squared dr dt. And here's the details on how to do that. Right? So I'm going to pull out the 4/3 pi, and then I've got t and r here. So I need to do the chain because I need this t, I need to convert it to an r. In order to do that, I also have to do this. So I wind up with a little bit of baggage here. And remember, this is a constant, but it's a constant being multiplied, which is different than a constant all on its own, right? Here, up here, these are constants that are on their own with a plus and a minus, right? They go to nothing. They're 0. But here I've got constants being multiplied, so they just hang out. And then what I'm going to have is 4 pi r squared dr dt, which is the thing I wrote right here. Now I sub in. So I've got, let me explain this notation because people were confused this morning about this notation. What I'm doing here is I'm doing r when v equals 4 pi over 3. So that's what that notation means, right? I've got r when v equals 4/3 pi. How do we feel about that piece of notation? 1 to 5. So this is just the notation. Okay. And if you're going on in physics or economics or something like that, chemistry, you're going to want to learn this notation because it's actually, especially when you have curves that aren't necessarily functions at all points, it's actually pretty convenient. And what I want is dr dt where v is 4/3 pi. So this says right here, the change in r with respect to t when v equals 4/3 pi. Well, I've got the wrong thing, right? I have the volume and I need the radius. So now I need to solve for some snapshot data. So what I'm going to do is I'm going to plug in here. I'm going to plug in 4 pi over 3 for volume. And I'm going to solve for this r. And this is nice because everything cancels. And I wind up with r equals 1 equals r cubed, which of course means r equals 1. So I plug that in here. I get 2 equals 4 pi times 1 squared. There are my units. Times dr over dt when r equals 1. I should write down this when r equals 1. So I get that the radius is expanding, and then I want to write something at the bottom here to say which way I'm going. So I say the radius is expanding at a rate of 1 over 2 pi feet per minute as the volume increases. Or when the volume equals whatever it is, or whatever as it's increasing. So that's kind of how I put this whole thing together. So how do we feel about this whole problem thing 1 to 5? What is this? Problem 3? Okay. All right, well, let's say the big thing you need to take away from what I'm about to show you is don't leave this problem blank in the test because they can run into this one I have out of 10 points, but they can run up to 14, 15 points. Okay? And you don't want to lose a letter grade and a half on this problem if you can't figure it out. So let me show you what the rubric for these things tends to look like. All right. This is the main part of the rubric, and you can see I've kind of laid it out here. You get 2 points for taking the correct derivative. You get 2 points for attempting the correct derivative, right? So you knew to take the derivative of volume with respect to time. All right, I don't know what it's doing. I'm not touching. I'm glad that's working so well. So this is kind of, you knew what to do. All right, and then you did it correctly. That was another 2 points. You saw for the snapshot data, that's 2 points. You kind of neatness, put everything together, 2 points. Your answer being correct, 1 point, 1 point for having the rubric, for having the unit. So there's the 10 points. Now, there's all this partial credit here. So you get, for without even touching the derivative, you can get up to 4 points or half the points you missed, whichever's less, right? So if you only forgot your units, you're only going to pick up a half a point on the partial. But, for each variable, you kind of list, say it's moving that, you can get it up to 1 each variable. 2 points for a picture, 2 points for all your labels and arrows. Okay? So, and this is kind of typical. So out of 14 points, the cap will probably be 6. Maybe 5, but 6 on this partial credit without even taking a derivative. All right? And that can make a huge difference in your test grade. And then you've got the equation there. Just, take a derivative. That's the motto for the test. When in doubt, just take derivatives of everything. So if you took the derivative and did it right, there's another 4 points. So you can actually, even if even if you're not setting up the problem correctly, perfectly, don't like freak out about the problem or sit there and try to figure it out forever and run out all your time. Come back to it. But, when it's, 20 minutes left on the clock, draw a picture, do some labels, and call that your problem. Take the derivative of both sides, right? I mean, does that make sense? 1 to 5, how do you feel about that? The importance of not leaving this problem blank. And last semester, what I would actually do was I wouldn't let you leave the test early if you had left this problem blank. I was like, no, go back, write something. But I can't do that this time, right? I can't be there in your living room saying, are you sure you want to turn it in? Are you sure you don't want to do that? I give them the look. Don't you want to spend some more time on my test? You have to give them the professor look. That's important. Okay. So that's really important. Don't leave it blank. Do some doodling. List some variables. All right, are there any questions about this? To answer the question earlier, for the stuff from test 1, you need to remember how to do limits and stuff like that. But the big thing you have to do is remember the definition of the derivative. 2 cops and a drunk doesn't show up, usually, unless she's absolutely changed everything. The usual thing is that 2 cops doesn't show up. But it does show up on test 4. So I would definitely keep it. That's why I put it on the bootleg, right? I want to keep it in the brain a little bit. Those popcorn limits can show up on test 2. Definition of the derivative can show up on test 2. Stuff like that. And of course, the graphing problem has stuff from test 1 as well. Okay. All right, so let's look at this problem set here. Let me pull it up. All right, so the way this problem set is set up, make sure you see it, is that there's three questions, right? One of them's a 6-parter. What I want you to do is I want you to list your steps here that you have for solving them. I want you to talk among your group about it. And then there are 6 of these related rates problems. You need to do 3. I encourage you to do a few more, but you have to do 3. Okay? One of them is off the test from, I think, 2 years ago. Oops. This one's from the book. This one is the one from peer leading. The second problem, the cone. This one here, I think I put it on a test last year. I think I put it on springs of last year, or on the makeup. This one was 2 semesters ago. And is similar to one in the book. This one is on the bootleg. We've never put it on the test. We have put it on the business calc test. And then for question 3 here, I want you to rewrite your steps and say, did they change? Did they not change? Even if you keep the exact same steps. Don't say, didn't change the steps. You'll get 0 for that. All right? List them out again. Are there any questions about that? Okay.